Hello, everyone. I hope I'm audible. Hello, everyone. Thanks for coming to my talk. It is so great to be in this picturesque city of Krakow and to visit Poland for the first time. I'm very excited, especially meeting the very interesting attendees here and participate in this free exchange of ideas. I could not be happier to be here. The title of my talk is Effective Data Engineering Using Higher Kind of Types. In this, I basically wanted to present a common purpose framework to deal with heterogeneous data environments and variety of data frameworks and use all of them to do the job that you want. And how do you do it well? How do you do it effectively is what I'm going to speak to you about. Hopefully this will be helpful to someone. And I'm happy to participate in other ways of effectively managing your data pipelines. So we'll start with just taking a look at data ingestion volume at Uber specifically. I'm sure this is the case with a lot of other companies. Not at a liberty to share the exact numbers here, but we are looking at trillions of messages per day, petabytes of data volume per day, tens of thousands of topics, and tens of clusters in 3 data centers that are all replicated. That means sometimes you have regional clusters, sometimes you have aggregate clusters, but suffice to say that there is extreme amounts of data coming from all directions, and they're being ingested into Uber's platform every single second. In this scenario, rapid data engineering really becomes essential because we want to catch up with this amount of data that's been ingested into the system. Why is data engineering essential? I'm sure a bunch of people can appreciate it. It lets you prototype ML applications offline. It lets you enable real-time ML applications so that you can apply inferences on the fly. It enables you to perform analytics on the data that you've collected in the past. And it enables data-driven business decisions. So data engineering, in a way, has become the backbone of a variety of business critical needs that a company has. So it's not enough to just process data efficiently in batch scenarios. You also have to write real-time pipelines. And yes, there are environments where you have like one framework that everybody understands and everybody conforms to. But more often than not, companies are going to deal with heterogeneous data environments. More specifically, in our case, we are using Apache Flink and Apache Spark extensively. Apache Spark for its batch engine for analytics, and Apache Flink for stateful, on-the-fly data stream computations. So for all of the examples that I'm going to share with you today, I'm going to focus on these 2 frameworks. But the ideas present here are not specific to the frameworks. They can be extended to any framework of your choice. And the efficiency of data engineering should be extensible. That's the whole point of why we should be writing common purpose frameworks in the first place. So what are some of the problems that you have to deal with when you're dealing with such a heterogeneous data environment and a very rapid data environment at that? First of all, you have to, again, deal with disconnected data frameworks. Kafka streaming, Spark streaming, Apache Flink, Apache Spark. There's a bunch of homegrown tools that we have at Uber that also process data on the fly. So they are all disconnected. They're not homogeneous to each other, either in terms of programming language APIs that they expose or in any other terms. When you write your pipelines, there's a lack of common code base. What happens is, more often than not, your application becomes hostage to the framework that you're using in order to write your data pipelines. So not only do you have to conform your business logic into the exact data framework that you're dealing with, you also have to do it multiple times because you're writing several kinds of pipelines. Thirdly, there's a lack of coherent integration testing strategy. By integration testing, I do not mean running your logic onto different data frameworks at the same time. By integration, I mean here's the input of data, and here's my business logic, and here's the output. Does the output conform to input? that kind of testing by completely isolating your business environment from specific data frameworks is something that's very tough to get to. And the last problem I also wanted to give some credence to was when you write data pipelines, you're obviously interested in metrics, and you're interested in logging, and you're interested in tracing. Well, at Uber at least, there are these three pillars of system monitoring: logging, metrics, and tracing. And when you're writing pipelines on different frameworks, now it is up to you as a developer to also conform to the metrics, tracing, and logging infrastructure of a company. So it becomes really tricky to deal with all these problems at once. So first of all, before I get into an example of a set of transformations that get applied to this ingestion stream of data that's been ingested continuously into the system, I'm sure you're all, maybe I should have asked it in the beginning, I'm sure you're all familiar with what Uber is, right? It's a ride-sharing platform. I know it is in Krakow. I took an Uber to get here today. But the example that I want to present today is, imagine there are riders and drivers' phones associated with a trip. And the phones are generating a lot of events on the fly. And each trip potentially can generate tens of thousands of such events. Now, it doesn't really matter what those events are, and we are not going to go into what kinds of events Uber is interested in processing on the fly. Suffice to say that there are some events that are happening on the trip that you want to ingest into the system, do some maps, do some flat maps, do some joins, and ultimately get the view of the data that a data scientist would be interested in, and a data analyst would be interested in, or an engineer would be interested in. So let's look at this example for a quick second. For a second, let's forget about what is on the left and the right side of this picture. We are interested in events from 2 different days. We unionize them. So now we have a combined view of the trip events. And then we group them by trip UUID, meaning the events are basically coming from all kinds of trips at the same time. But you want to see them grouped by trip UUID so that if you're interested in a particular trip, you can see the canonical arrangement of events that appeared from that trip as one block of data. Then what we do is, there's another data source. Doesn't matter what it is. It could be a Hive table. It could be a Postgres table. But that table stores some metadata about the trip. And in order to get the complete view out of the trip, you have to do a join between the grouped trip events and the trip metadata. Once you get the joined trip events and trip metadata, you perform some sort of aggregation logic and arrive at a view of the trip that you're interested in. This is not to say that every pipeline basically follows this structure. It's just to illustrate a point of what kind of pipelines we're writing. The yellow parts are data sources. The purple part is the data sink. Now, the interesting thing to notice here is, it doesn't matter whether the data source is a stream and a data sink is a stream, or data source is a Hive table and a data sink is a Hive table. All that we are interested in as data processing engineers is performing a set of transformations that is not specific to whether the data is coming from batch or streaming. Let's look at another example. It's quite similar to the first one, but just to illustrate the point, you can see that it is slightly different. So again, there's a data source and data sink. In this particular case, we are not interested in events from 2 different days. We are interested in events from the driver's phones and the rider's phones. Group them by trip UUID. Now you have a view of all of driver events grouped by trip UUID and all of rider events grouped by trip UUID. And you're interested in joining them together because now you want to see what happened on a trip viewing from 2 different devices. Once you have done a join, you again apply some map of aggregation logic, and then you get a final view of the trip. So just to, okay, so this is example 1 and example 2. I'm sure Some of you have seen this code before. Functional languages give you a powerful way to abstract your ideas. Why are we interested in abstraction, though? Because all problems in computer science basically demand that you find a way to indirect your solution to a problem of higher abstraction. And this is a quote from a computer scientist that I admire. All problems in computer science can be solved by another level of indirection, indirection being the key word. I know that domain-driven design is not necessarily something that everybody likes. Maybe some people are familiar with the talk that happened yesterday. I'm not a proponent of domain-driven design, but one thing that I really like from that idea is that expressing software in terms of what the business demands is always a better idea, because your data frameworks can change, your environments can change, but the business more or less remains consistent. So writing software against business language is always a better idea. So the heart of software is its ability to solve domain-related problems for its users. Fair? So what are we interested in here? Before I go into this solution, can I gauge a familiarity of data frameworks just from the audience present in the room? How many people here present know what Apache Flink is? Yeah, that is expected. And how about Apache Spark? More of you, that's fair. But when I say the word data container, I want to just capture the abstract idea of a data set from Spark or a data stream from Flink. So if you look at what the environment is and what kind of solution that we want to have, there's business logic on the top, and there are these all data providers. It could be a data stream from Flink, it could be a data set from Spark, it could be some in-memory data, it could be some file on local disk, doesn't matter what it is. It's a source of data, source as in data source. And there's business logic on the top. How do we write a connector so that the business logic doesn't need to be repeated? We need business-specific transformations on these green boxes, which are the data containers. And we also need connectors that can fetch data to fill up our data containers from all these variety of sources. So those green boxes is what we're interested in. How do we achieve that? First of all, the data container could be plugged to the framework-specific data provider. That means it could be plugged to a data set and data stream and in-memory lists. For the purposes of illustration, we'll just focus on these base data containers. But I hope you can get the point that this could be extended to any other data framework. For example, Spark streaming, I don't even know what kind of primitive it exposes. Maybe a data stream like Apache Flink. But the point is, a data container should be able to connect itself with the framework-specific primitive of data container. The second property should be that it could hold a bounded type. A lot of data pipelines, I would accept here that a lot of data pipelines, even at Uber, would not be written typed to the exact bounded type. And that would mean a lot of hand wrangling when you're reading row out of a Hive table or when you're reading an event out of a Kafka topic. So the second property that we demand out of our data container is that it should be able to hold a bounded type. So a container of a driver trip event versus a rider trip event versus something else. And thirdly, the data container should support common transformations that produce another data container. Because of the nature of audience that I'm talking to today, I hope everyone is familiar with what map is, what flat map is, what group by is. After all, our business logic is also based on these primitives. We want to look at some stream of data, and every event that we see there should be mapped into something else. Or if every event produces another list of events, we should be able to flat map that stream into something else. So in order to come up with the data container, I demand my container to provide me these three basic properties. Um, for this talk, I'm just going to stick with one language, which is Scala. But Scala has in-language support for higher kinded types. If you're familiar with generics, generics is a type constructor that works on a bounded type. A higher kinded type is just generic at a higher level, meaning it is a type constructor that works on a type constructor that connects to a bounded type. It was introduced in the Scala language as part of this paper. Maybe if you want, you can go through it in detail. That's the link. So here's where we start our implementation. First of all, we'll live with this domain object. Again, domain object being the term that's coming from the DDD side of things. A domain, of course, for brevity and also for illustration purposes, I have removed all of the complexity from a trip event, what kind of details are associated with an event. Suffice to say that it has a trip UID and some secret values. And on this data, on this domain object, we want to have DataContainer connect to the framework-specific primitives of data providing. So a trip event reader, as you can see, is bounded to a higher kinded type, which is DataContainer. That is the syntax for a higher kinded type, by the way, just a square bracket with an underscore inside it. So it's not bounded to a specific type yet. It would be bounded to a specific type later. So we can write a reader and writer for our trip events by directing the read and write methods on the DataContainer instead of a data stream or a data set. So that's how I write a connector. How do I bound this connector to Apache Spark? This is where some of the messy code is going to start to show up. But if there is a data set trip event reader, the promise is that it would give me a data set of trip event. But the good part is that both Apache Spark and Apache Flink read and write methods can conform to the same interface. How would it look for Apache Flink? Sure, some complexity going on inside the read and write methods, but still conforming to the overall type that the DataContainer demands. And how would you connect your DataContainer to a in-memory list? Simply by reading and writing lists. So just based on these very simple principles, what we have been able to achieve is this bottom layer. We were able to abstract out the DataContainer from variety of data sources and the primitives that they work with. In case of Apache Spark, a data set. In case of Apache Flink, a data stream, a list, something that comes out of a file, doesn't matter. But we were able to achieve that red layer just by that simple design. What's the next piece here is to achieve the layer on the top, which is business-specific transformations that are bound to DataContainer. How would we implement that? Well, right now, I would just focus on 3 simple operations that are very universal, and I hope everybody is familiar with at least the concept of map, a flat map, and filter. So if you look at the mappable container trait, it's connected to a higher kinded type, and it promises to expose just one function, which is map. I hope the signature of map is familiar to everyone. It's just an input data container and a function that takes the type of that data container and maps it to a separate type and produces a data container of the second type. I won't go into specific details of what flat map is doing and what filter is doing. I hope the function signature itself is sufficient. But what do the transformations bounded to Apache Spark would look like? That's what we are interested in. Well, the good news is that a framework like Apache Spark has built-in support for map, flat map, and filter. So you can simply bind your map definition to Spark's map definition, and your flat map definition to Spark's, and so on. If you feel like these examples are looking a little more contrived, Yes, they are, but we'll get into the complex transformations in a minute. How do the transformations look when bounded to Apache Flink? Very simple. Flink provides map, flat map, and filter. How do they look bounded to lists? No points for guessing. Scala lists provide map, flat map, and filter. But here's the tricky part. And we are going to get into some messy implementations of join logic, for example, on these three different data providers. So the signature of join is fairly simple. Of course, the actual implementation of join in different data frameworks can depend on what kind of join you're performing, outer versus inner join versus in streaming, is it a tumbling window join versus a timed window join? Doesn't matter. A join is basically two different data containers that come together and produce a third data container of a third type. So data container of X, data container of Y, or U and V, and that produces a data container of X. But how does the join look when you're demanding the join from Spark? There is a join API from Spark, but depending on what your business logic join means internally, you can use an implementation of Apache Spark to provide the join connector to your data container. So the pieces, the portion of the code in yellow here is basically something that you shouldn't even bother about, because the ultimate goal is to get an implementation of join for our business logic from Apache Spark. Here's the transformations bound to Flink for join. Again, the implementation here just happens to be for tumbling window join. It doesn't matter. It could be some other kind of join. The good news is the join API on our data container was totally supported by Apache Flink, using some hand wrangling, but for good reason. I was actually very surprised how hard it is to do joins on simple lists. Again, it doesn't need to be explained what's happening right now. Suffice to say that the yellow parts are basically the hand wrangling for implementing a join on plain Scala lists. Well, what did we achieve out of all of this? We are now able to provide that layer that implements the transformations specific to the business logic that we want. So far what we were able to do is implement both the data framework specific connectors and the business logic specific transformations connected to our data container. I was really surprised to see that my business logic now only needs one implementation. And that's why we went through all this exercise, because I am interested in, if you remember the diagram, the couple of examples that I showed you initially, I'm only interested in doing that. I don't care whether my data frameworks give me a data stream, they give me a data set, they work on Hadoop, they work on Spark, Spark streaming. We have some internal implementation of streaming frameworks, as I told you. But I'm not interested in any of that as a data engineer. All I'm interested in is I have some set of business transformations to perform, and I only want to write my code against that transformation once. Doesn't matter what the detail is there. That was the set of transformations that I was initially interested in. And I achieved a single code base for that set of transformations. Now, when I'm deploying an Apache Flink pipeline, I just tie it to the Apache Flink connectors and transformations. And when I'm deploying an Apache Spark pipeline, I would just deploy the implementations for the Spark connector and transformations. And this is in my experience, writing pipelines is one thing, but when data scientists demand very stringent data quality and data coverage checks, it becomes a nightmare. But using this approach, I was able to simply swap out Hive or Kafka for in-memory lists. I'm a big fan of quick check. John Hughes is here. I could now write property-based testing against my business logic. and the transformations that I do in order to take certain set of data containers into another set of data containers. I won't bore you with testing logic or code, but when you have access to a data container that's represented in in-memory lists, it's very easy to inspect it, transform it, see what's going on, and simply do property-based testing. I want to input such and such streams of data on one end, and I want to get such and such stream of data on the other end. Is it happening for a variety of different data scenarios? So let's look at the problems that we started with. We had heterogeneous data environments. Our problem kind of solved that. I mean, you still have to write the transformations and the connectors for a specific environment. Of course, you have to. It's not going to happen by magic. But we now don't care which data environment is our data coming from. We have actually completely abstracted out our business from the dependency on a specific data provider. Second was the lack of common code base. And I want to touch upon this a little more in detail. Maybe in other companies it happens the same way, but at Uber we have schemas, data schemas. And there's an internal schema repository where you would define your schema, place it, and it would be a non-destructive schema, meaning you'll always be required to provide a backward compatibility on every schema that you own, meaning you cannot remove a field once you've introduced it. You can make it nullable, but it means that your schema is basically always moving forward. The problem that introduces with our data pipelines is that once I have changed my schema from V1 to V1.1, and let's say right now I'm only interested in the streaming pipelines, and I change my schema, what that made happen was because my schema is only backward compatible, not forward compatible, all of my bash pipelines just broke down. Meaning, I fixed one problem to address something that a data scientist wanted, but I created another problem for a data analyst because they're only interested in the batch pipelines. And changing schema shouldn't matter, it shouldn't mean that one has to break the whole pipeline. And that's what I meant by it goes back to the integration testing strategy, and also the fact that we have to live in this constantly changing data environments and also constantly changing states when it comes to schema. And lastly, again, like I mentioned before, there's metrics, tracing, and logging. Because you're now writing all of that against a common data container holder, you don't really have to implement it again and again. You can implement your logging, metrics, and tracing for the data container, and that too just once. By the way, at Uber, we have a really good library for tracing. I hope people are familiar with Open Tracing API. And there is an implementation of Open Tracing at Uber, Jaeger. Please check it out. It's from our observability team. It's very, very nifty. I would say that we get 4 stars on these problems because we were able to address these problems very specifically and very surgically. But here's the interesting part. Who's just interested in writing data pipelines? I, being a functional programmer, I'm interested in compositionality. Because my data container implements map and flat map, guess what it provides me as a free perk just for implementing map and flat map? Any people in the audience who are familiar enough with Scala for comprehensions? No worries. So basically, for comprehension in Scala is much like do notation in Haskell. All you have to do is provide the map and flat map implementation for your type, and you can simply do for comprehensions without any extra work. So you take a data container, and then you do a for and a yield on it, and it now becomes available for free on your data container. Don't even have to implement it. I didn't have a very dense or long talk. The conclusion here is that functional abstractions are really powerful and great when it comes to providing a layer of clear reasoning on top of the heterogeneous data environments. And even though I chose the backdrop of data environments, functional abstractions, I would believe, are almost essential for writing good composable software that you can extend, that you can have your business logic expressed against. Because as software developers, we are in search for reducing duplication, reducing complexity. And all of that is very easily achievable through functional transformations and abstractions. I can answer any questions that you might have, but just a plug, we are a huge data engineering team, and we are always hiring. So hope to see you guys sometime. But I can answer any questions. That was my talk.
Okay, we have plenty of time for questions.
Hi, thank you very much for the talk.
Thank you.
I was feeling like, yeah, we are having all these problems. That's amazing to see someone else facing them.
Very glad to hear that.
Yeah, and it was very, very interesting. So you show there like the simple use cases, map, flat map. For the join, you didn't give very much detail, but there are many more things, right? How you abstract these things. Like, for example, persisting data sets, running a bunch of operations on them, and many more things. So I guess you already found all these problems. Where could we find more details?
So I was not lying when I said that I chose these examples in a more contrived fashion. Of course, the point here was just to illustrate with three very basic examples of functional transformation that most people understand. But you're right. You have to write specific implementations for each kind of complex operation that you're interested in. Well, in this case, the two examples that I showed you, map, flat map, and join, were good enough. But I think the second part of your question was about how do you connect the readers and writers to specific data frameworks?
For example, you want to cache some data set in Spark,
Cache?
run a bunch of operations, and then unpersist it. For example, this is another more complex example for how will you apply these things.
Okay, so if I understand it correctly, yes. If you want to, for example, checkpointing is a very common operation that you do on Spark datasets. You can cache it, but the good part is that you don't have to anomically introduce your that logic into the business part of things. It just remains on the outskirts. Going back to this diagram that I had initially, we want to keep all of that specific into these two flat layers, so that our business logic is completely free of it, and our data container implementation is completely free of it. Because after all, we're interested in limiting the complexity to just the parts that it belongs to. Hopefully that answers.
Okay, so I see that you cannot put this into a common library that everyone uses, but for every specific case, you separate your domain logic from, and it's specific for your code base, right?
Absolutely, that's the idea.
Thank you very much.
Thank you very much.
Thank you for your talk.
Thank you.
My question might be because I'm not familiar with Scala.
Sure.
But it seems that in flat map, you map a value, you need a function that maps a value v to an iterable of something else?
Yes.
Why not map it to a container so it will have
okay, that's a very
kind of structure?
Salient point. It feels like you actually saw the example signatures. That's great. Yeah. You can do that. You can have a flat map function that has a signature of an input data container and a function that takes an individual item in the container to a different container. For the sake of simplicity here, I just kept it to iterable because most flat map operations are the functions that take one event to a stream of events is mostly contained in memory. So Spark, I think, has an implementation of a flat map that takes each element in a data set and maps it to a new data set. But that basically would mean that you have to do the redistribution of that data set on the cluster. And I mean, do we really need to capture that in the business? Possibly not. So I just kept it to iterable.
Okay.
Yeah,
I see.
but you're right. Like if I have to be pedantic about it, I would implement a flat map implementation such that the function actually takes it back to the container type, the actual container type, not necessarily an iterable. Thank you for asking.
Thank you.
Any more questions? Okay, so let's give Animesh a closing round of applause.
Thank you.